Okay. All right, we're going to take a look at Aldol Additions now, which is section 21.3. And something that we saw earlier on in this chapter is that if you take an aldehyde or a ketone that's got alpha protons and you treat it with hydroxide, like sodium hydroxide, or an alkoxide, like, methoxide or ethoxide, we saw that there was an equilibrium, didn't we? And we saw that in that equilibrium, you had some of the actual aldehyde and you had some of the enolate as well. So technically, when you take acetaldehyde, which is the name of this aldehyde, and you put it in sodium hydroxide, you've got some of this and you've got some of the enolate as well, right? They're both in the reaction mixture. So what happens is that you've got a good nucleophile, right? You've got a good nucleophile here and you've got an electrophilic center there. So now there can be a reaction between that enolate and that aldehyde or ketone, okay? And you notice that that's what looks like what is being formed here in this reaction that we call an aldol addition reaction, is that the enolate is going to attack the enol like this, and then after a proton transfer, you get this compound here that you call an aldol. Now, where does that come from? You've got the features of an aldehyde and an alcohol in the same compound, and that's where we get the name aldol. I think I misspoke at the beginning because I said aldehyde or ketone, and I should have just said aldehyde only. Well, let's take a look at what happens under basic conditions. You deprotonate the aldehyde at the alpha position to give you the enolate, right? Here's our enolate right here. They've drawn it with the negative charge on the carbon, and they're showing you the nucleophilic attack. Then there's a proton transfer at the end, and you end up with your aldol, okay, which again has the characteristics of an aldehyde and an alcohol, and we call that an aldol addition. Pretty cool reaction, huh? Where you start with one starting material and you cause it to react with itself, really, is what you're doing. It's very interesting. Now, the aldol addition process is an equilibrium process. For simple aldehydes, okay, if you have a very simple aldehyde, the aldol product is going to be favored, right? You see here that at equilibrium, we have, 3/4 the aldol, and we have a little bit of the aldehyde left over. But if you have something like a ketone, generally speaking, the aldol product is not going to be favored. So at equilibrium with a ketone, you actually mostly have the ketone in equilibrium with very little of the aldol. Okay, so something to kind of keep in mind here when we're talking about aldol additions. Well, it says here, and I'm just reading off the slide, it says the reverse process is called the retroaldol reaction, because remember, we're in equilibrium here. So what would the mechanism be for the backwards reaction or the reverse reaction? It's literally just the reverse of the aldol addition. First, we have a proton transfer, then we lose the enolate as a leaving group, and then the enolate can pick up a proton, and you end up with your carbonyl compound in this case, okay? So there we go. We have the product, the retroaldol, or the product of the retroaldol reaction. Now, when an aldol product is heated, okay, because everything that we've looked at so far, if you look at these reaction conditions, no heat here, no heat here, whenever everything that we've looked at so far hasn't involved heat, but when you add heat to the situation, whether you're doing the reaction in basic or acidic conditions, you end up with an alpha beta unsaturated carbonyl compound. Okay, so an alpha beta unsaturated carbonyl compound, and we saw how to make alpha beta unsaturated carbonyl compounds earlier on in this chapter, but now we're looking at it in terms of an aldol reaction, and we call this an aldol condensation. Why? Because you take your original aldol product, and you end up losing water when you make the condensation product, right? The way I remember this is if you're heating it up, okay, well, what does heat cause water to do? It causes it to go away. It causes it to evaporate. So that's how I remember that I get the condensation product. So again, the aldol condensation product occurs when the aldol addition is performed at elevated temperatures. Okay, so you've got to have heat in order for the aldol condensation to occur. Well, let's take a look at what's going on here. We have acetaldehyde, okay, If we're doing an aldol addition reaction, that's at room temperature. Okay, for that, let's say we would use like sodium hydroxide, and water, okay, to do the aldol addition. But if we want to do the aldol condensation reaction, we would use like sodium hydroxide, water, and we would heat it up. Okay, so we need more vigorous reaction conditions. And the driving force of this reaction is going to be the formation of the alpha beta unsaturated ketone. What makes it so great? Well, if you check it out, you see that it's conjugated, and that adds to the stability of the molecule. So that, again, is the driving force, is the formation of that conjugated compound. Let's take a look at the mechanism here, okay? The first part we've already seen, okay? To do the aldol formation in base, we simply do a deprotonation, which is a proton transfer. Then we have our nucleophilic attack proton transfer, and we end up with our aldol. So when we're in a high heat situation, what we're going to do is we're going to remove this proton here, and then we end up losing the hydroxide as a leaving group. Keep in mind, we are in base. All right, and that gives us our alpha beta unsaturated carbonyl. Now, in terms of the stereochemistry, when there's two stereoisomeric pi bonds that can be formed, whichever product has the less steric interactions, that's going to be your major product. And we're not going to look at anything beyond that. Just your major product is going to be having whichever product has the least steric interaction. So in this case, it happens to be the E compound, which is trans, and the minor product happens to be the Z compound, which is cis. Anyhow, there we go. Now, because aldol condensation is favored, right, all you have to have is really a slightly elevated temperature. Oftentimes, it's impossible to isolate the aldol addition product. So let's say you take acetophenone and you treat it with sodium hydroxide. You really can't isolate this because the reaction is just going to drive forward to make this fully conjugated system. You see that all of everything that I have highlighted in yellow is fully conjugated. So that's going to just push the reaction forward to make that conjugated system like that. So again, aldol condensations, their yields tend to be much higher. If you look at this reaction that we looked at just a few minutes ago, we said, okay, you take, cyclohexanone. You can form the aldol at room temperature or low temperature, 10 degrees Celsius. I mean, it's a little lower than room temperature. And you end up with what? 1/5 of the material being converted to the aldol. Whereas if you turn it up to just 100 degrees Celsius, that's pretty easy temperature to obtain. You get the condensation product in a good yield. And again, it's because you not only lose water, you form this conjugated system here. That is the driving force behind the reaction. Now, if you're very astute, you might be wondering, well, that's all well and good, but what happens if I have an aldehyde or two aldehydes that are different, right? Here I have acetaldehyde, here I have propionaldehyde. What would happen if I took both of those and I treated them with sodium hydroxide? Because I would end up with, I'd get this enolate, okay? But I'd also have this enolate. So now I've got a mixture of what, 4 compounds? What the hell is going to happen then? I've got so many different compounds. Well, then you get what's called a crossed aldol condensation. Literally every possibility is going to occur, right? These two are going to combine to make this aldol product, right? These two are going to combine to make this aldol product. You're going to get this aldehyde with this enolate to produce this product. And then finally, you can see where I'm going, right? You're going to combine these two to make this compound. So you get literally every combination, and we call that a crossed aldol reaction or a mixed aldol reaction. Now, again, if you have 2 different aldehydes, you get 4 possible aldol products. You can imagine what I'm going to say next, which is this isn't the most useful reaction we could think of, is it? Something where you get that many different products. So there are ways that we can actually do a crossed aldol reaction, and we can harness its power and make it a useful reaction. Okay, it says here that crossed aldol reactions are really only practical if the number of products can be minimized, right? We don't want 4 different products. We want to have like one product or something like that, okay? So here's how you do it. There's 2 ways that we can minimize the number of products, okay? 2 ways. Number 1 is if one of the substrates is relatively unhindered and has no alpha protons, right? So this compound, formaldehyde, it's got no alpha protons. It cannot be deprotonated. So therefore, the only enolate that you would form in the reaction would be this, okay? So really, you're only going to get, that enolate reacting with the formaldehyde. Okay, so that's one way to limit it. Now, I know what you're thinking. You're thinking, well, if I put this in sodium hydroxide, I'm going to have this compound and I'm going to have its enolate. Like, couldn't that give me 2 total products instead of 1? Well, there are ways to control that, okay? What you would do is you could add this, since this is so unhindered, it's going to react faster than this would. And so you probably would get a mixture, but you would get mostly this, okay? Let's see. What I think is an even better option is not covered until here. So I'll talk about it here. Anyhow, it says this is possible when only one compound can form an enolate and the other compound reacts with the enolate faster. So here we have, again, only one possible enolate, and it's going to react faster. So we're going to get the reaction with benzaldehyde, and then this is just going to be a runaway train. If you heat this up, you end up with a fully conjugated system like that. So that's one option. Okay, so to repeat, option number 1 is one of the substrates is unhindered and has no alpha protons. So we don't have any alpha protons here. So that's one way to minimize the number of products. And a way that I think is even more interesting is to use what's called a directed aldol addition. So what you would do is you would take your aldehyde or ketone, you treat it with LDA, right? Remember, that's a really strong base. You're going to get complete deprotonation. Then what you do is you have this in your reaction mixture, right? You have the enolate in your reaction flask, and then you add this slowly to it, drop by drop by drop by drop. And as soon as this guy touches this, boom, it's going to react to give you this immediately, right? So that's what the idea is behind a directed aldol, is that you make one enolate completely, and then you add the other aldehyde to it so quickly, and then it's going to keep doing nucleophilic attack after nucleophilic attack, and that's going to produce one aldol product. Directed aldol condensation or a directed aldol addition, really powerful, powerful reaction. Anyhow, there we go. So now another option is to do an intramolecular aldol reaction, right? What if you have 2 carbonyls in the same molecule? Like here we have a compound that has 2 carbonyl groups in it. We have, 1, 2, 3, 4, 5, 6 carbons in our diketone, but the carbons, or the carbonyls rather, are 1, 2, 3, 4 carbons away. So why couldn't I deprotonate, at one of these alpha positions to make an enolate on one of the carbons, right? And that's what's being shown here. Now you might be asking me, well, Mr. Dion, there's more than one type of alpha proton here, right? What if I deprotonated here, right? Couldn't I do that too? The answer is yeah, you could. But if you were to do that, the nucleophilic attack would result in the formation of a 1, 2, 3 membered ring, which is really strained. And so we're only going to get a nucleophilic attack occurring that's going to produce a 5 or 6 membered ring. Look what happens here. When my nucleophile attacks, right here, I've got a total of 1, 2, 3, 4, 5 atoms in my ring. So after the condensation occurs, I end up with this 5-membered ring with an alpha beta unsaturated carbonyl. Okay, so that's an intramolecular aldol reaction. Question 21.14 asks us, predict the major products when each of the following aldehydes is treated with aqueous sodium hydroxide. Notice it doesn't say anything about warming it up. There is no mention of heat here whatsoever. So I'm going to write that down here. No heat. That means we're only going to make aldols. So this is aldol addition conditions because there is no heat. So why don't we start by drawing out the enolate that would be formed when we treat this with sodium hydroxide. And remember, we're only going to get partial formation of the enolate. But I'll draw it like this. So it's going to look like that. And we have a negative charge here. Just going to put brackets around it like that. Well, this enolate is going to be able to react with this carbonyl here, okay? And after the proton transfer, so I'm going to draw two arrows here because we have the nucleophilic attack, then we have the proton transfer. What am I going to end up with? All right? There's a number of ways that we could write this out, but I think an easier way to maybe write this, I'll delete some of this stuff here, is if I do it like this, where I draw, there we go, like that. So I'll put the phenyl here, put the negative charge here, and draw my nucleophilic attack like this. Then my aldol addition product becomes a little easier to draw. So I have all these carbons here with my phenyl. Now my new bond, this is my new bond that I formed with this curved arrow here, okay? My new bond is attached to what? I've got, after my proton transfer, I have the hydroxyl, then I have 1, 2 carbons, so 1, 2 carbons, and then I have my phenyl over here, and there's your aldol product. So we end up with an aldol. Let's try the next one. We take this, we treat it with sodium hydroxide. There's only one possible enolate, right? Because this is the only alpha proton in the molecule. So I would end up with this enolate, the negative charge here, like that. Now that is going to do a nucleophilic attack. Okay, it's going to do a nucleophilic attack on the carbonyl like this. So after my nucleophilic attack and proton transfer, what do I end up with? Right? What do I end up with? I'm going to end up with something that looks like this. So draw my 6-membered ring. My aldehyde over here like this. Then I have a bond. This is the new bond that I formed. It's going to have a hydroxyl on it, and it's going to have the cyclohexyl on it like that. And there you go. There's my aldol product. I don't know why I keep doing that. There we go. My aldol product. All right. Let's take a look at an aldol condensation. So it says draw the condensation products when each of the following compounds is heated in the presence of aqueous sodium hydroxide. So we're taking sodium hydroxide and we're heating it. Now there's a really cool skill builder. It's skill builder, I wrote it down here, 21.3, which helps you to solve these aldol condensation problems. I'll show you my kind of shorthand of doing it. First, I'll show you the long way of doing it, and then I'll show you the short way of doing it. So the long way is to simply draw the enolate. So I'll start by drawing the enolate. I've got my 5-membered ring. Okay. And I'm going to draw my negative charge like this. Okay. And again, I'm only going to have some of the enolate because I'm in sodium hydroxide. So it's going to do a nucleophilic attack like this. Okay. So after my nucleophilic attack and proton transfer, what I'm going to end up with is something that looks like this. So I'll draw my 5-membered ring like this. There we go. I still have my carbonyl here. Here's my new bond that's formed. What's going to be attached to my new bond? I've got a hydroxyl, I've got a methylene, and then I have another cyclopentyl over here like this. So when I lose water, right, when I lose the water, I'm going to form the alpha beta unsaturated carbonyl compound. So I'm going to end up with this. Just try to draw it as neatly as I can. Here we go. So I'm going to have one cyclopentyl group over here. I have my double bond, and I have another CH2, and then I have my cyclopentyl group over here, like this. So this is the aldol condensation product. So this is my alpha beta unsaturated aldehyde in this case. But either way, it's an alpha beta unsaturated carbonyl compound. Now, the shorthand way of doing this is like this. I'm going to go over to a blank page here to show you. And once you see the shorthand way, I think you're probably going to like it a lot. So watch. Watch, and I'll show you the shorthand. So again, this is 21.17, and this is C. So we're taking this compound, okay, and we're going to treat it with sodium hydroxide, and we're going to heat it up. So that means we're going to make an alpha beta unsaturated carbonyl compound. So what you do is copy the compound. Okay, so I'm going to copy it, and I'll paste it over here. Okay, and then I'll take another one of them, paste it here. So what you do is this. You draw your alpha protons in a different color, okay, like this, and you put the molecule right next to the other the oxygen of the other carbonyl. Okay, the water that's lost to form the double bond is going to be these two hydrogens and this oxygen. And so the double bond, I'll use green pen. The double bond is going to be between here and here. Okay, so that's literally all you have to draw, and that is your alpha beta unsaturated carbonyl compound. So all you'd have to do is redraw this. Okay, you have the double bond here, and then you have CH2 in your cyclopentyl. So you could go CH2 and then put your cyclopentyl over here. But to make it a little less hindered, I'm going to do it this way. So CH2, and then my cyclopentyl group will be right here like that. And that's it. That's the product. Okay, that's the exact same thing I had written on the previous slide. Okay, let's try it again. So this time I'm not going to go the long way. I'm just going to show you the short way. So this is 21.17D. So D, we're taking this compound. Okay, we're going to treat that with sodium hydroxide. We're going to heat it up. So what we'll do is we'll copy and paste the molecule. So copy, paste. Okay, and I'm going to paste another one. Okay, now the molecule is symmetrical, so you can clearly see that there's only these two alpha protons here. Okay, so now we're going to take the molecule and we're going to move it so it's right next to the oxygen, like that. Now the water that we're going to lose, minus H2O, is going to come from these two hydrogens and this oxygen. So the new double bond is going to be between these two carbons, like that. So watch. All I have to do is redraw the molecule like that. I put a double bond, and I have 1, 2, 3 carbons on this side, and 1, 2, 3 carbons on that side, and there you go. That's the product. Okay, so that's, again, the shorthand way of doing it. And again, the skill builder goes over it in even more detail. I'll leave it down here in case you want to pause the video and study it or something. But that's how you draw the product of an aldol condensation. So again, these are aldol condensation reactions because we're using heat. Okay. So let's move ahead to 21.19. It's asking us to determine what would the compounds be that would be required for this aldol reaction to produce each of the following compounds via an aldol reaction. So the first one is an aldol This is, son of a gun. This is the product of an aldol addition, right? Because we end up with an aldol. And this one is an aldol condensation, right? Because we end up with an alpha beta unsaturated ketone. I think this one is actually simpler, the aldol condensation, because all you have to do is break this bond here. So in terms of retrosynthesis, what you need is cyclopentanone to start with, plus you need this carbonyl compound, which turns out to be benzaldehyde. So that's all you need is cyclopentanone and benzaldehyde, and you're going to treat those with sodium hydroxide, and you're going to heat it, right? And that's going to be the synthesis of this aldol condensation product, right? Okay. Whereas this one here, since it's an aldol addition, now if we were going to heat this up, right? If you heated this up, you would end up with the alpha beta unsaturated ketone right here, right? Because this is the alpha position of the carbonyl. This is the hydroxyl. So you would lose, to lose the water, you would lose H2O, and you would make the double bond there, right? So you can kind of think about it that way and say, okay, well, in terms of what I would need would be, I'm doing retrosynthesis now. So what would I need? I would need cyclohexanone, and then my carbonyl compound would have all of these carbons in it, right? So I would need a 6-membered ring with a methyl group, a carbon, and then that carbon would have a double bond like that. So it would be this aldehyde. So we can write it out a little neater than that now that we know the structure of the two molecules. So what would we do? We would start with our ketone. We start with our ketone. We would treat that with sodium hydroxide and water. Okay. And then we would put in the aldehyde. Should be this. I'm just drawing it a little neater than I had the first time, like that. And that would give us our aldol product. So aldol product. And over here, we end up with the alpha beta unsaturated ketone. Boom, just like that. And for today, I think we're gonna skip the next question, and we're gonna come back to it at the beginning of class on Friday. So I'd like everybody to try and propose a mechanism for this. We saw part of the mechanism earlier on, that you're going to form an enolate, which is going to do a nucleophilic attack like this. But I want you to see if you can draw all the curved arrows for this mechanism here to make this alpha beta unsaturated cyclic ketone.